We are starting our webinar on smart transportation. This is the fourth webinar, and I welcome every participant. We have a very exciting program today, so I will not take long. Claudia, Dr. Claudia Goldman is co-chairing with me this session, so I'll say a few words and then I introduce her to give the first lecture. So 2020 was not really a good year for transportation and mobility, as we know. However, goods moved around in the world, and you could see that transportation is a field that is here to stay. We are heading now towards a new era in smart and autonomous mobility, and our center focuses on various aspects of research, and we have a special professional committee on this, also chaired by Claudia and myself, which is called the Models and Algorithms part, which deals with all kinds of issues in modeling and developing algorithms in order to make mobility smarter and generate smart transportation solutions. This webinar has 5 exciting lectures in various directions in this field, and the first speaker is going to be Claudia Goldman, and I'm happy to introduce her. She is a very well-known and noted researcher in subjects of artificial intelligence and user experience, and she is a researcher with General Motors, with the General Motors Research Lab that exists in Israel, and she's involved in various interesting projects in this field. She holds a PhD in computer science from the Hebrew University and has held various positions over the years. However, I would like to give her as much time as possible. So, Claudia, please start your lecture and say a few words. And you can say also a few words about the center from the point of view of industry.
Okay, thank you very much, Freddie. Can you tell me if you see my screen first? So
yes,
I know that
we see your screen, everything is fine.
Okay. So thank you very much. As Freddie mentioned, I am with General Motors. I am a member of the user experience technologies, but coming from the computer side with a PhD in AI from the Hebrew U and a postdoc in UMass in Amherst. I am looking at ways to leverage what we know from AI, machine learning, in order to improve the user experience in all these automotive experiences that we know and we may have in the future. So specifically in this talk, I'm going to present results from a project we have done to develop an adaptive agent, in the sense that that agent is able of adjusting its behavior to its human user. So when we look at the current cars, when you enter a car and you think at the same time about what is the experience a driver might have while driving, basically what we see today is a set or a bunch of many different and very rich options of systems. But what is very salient here is that this is a system of systems. We don't see one holistic experience. And at this moment, I am not sure how much we can talk about intelligent interactions at the moment, but we are more talking about systems that a driver is about to operate. And very interestingly, when we look back in the history of automation, we can understand this development by looking at the human factors literature, where works have been done to understand how to develop machines for experts users to use them and operate them. So the main focus was in the operation of the machine. And in that sense, the vehicle is a machine that the driver is supposed to operate. So the first automation solutions were mainly developed to replace users in tasks that were very difficult or repetitive for them. And so this could make sense when we come to say, well, we are driving for long periods, it might become boring, maybe the car can replace you. Another interesting concept is the one that whenever you have a human and a machine, then the way that they can operate the machine is by a task division idea, meaning that it's either the user or the machine that will be acting. But if now we try to give a perspective from the AI side and robotics and human robotics interaction, we see that we can look at this experience in a totally different way. First of all, our drivers or passengers could be anyone, right? So it doesn't have to be an expert person like a pilot. So although regulation requires driving licenses, I think it's clear for you that it's different. A driver is a different profession, let's say, than a pilot. He's not working when he's driving. Besides that, persons are also involved in physical as well as digital tasks. And maybe the most interesting point I would like to emphasize here is that from the AI side, when we talk about interactions between users and machines, we also consider the machine as having proactive behavior, meaning that the machine itself can decide autonomously what it should do, when it should do it, and what is the value of it. And I think this is a very important point to understand how these experiences and interactions can become different. So one of the important points besides the way we perceive machines is that maybe it might sound trivial, but drivers and passengers are humans. And why is that interesting to us? Because now if I focus on the AI side, usually the work on that end was focusing on machines that are rational, meaning that they will be able to compute policies with maximal values. But when now we come to humans, this is not the case. So humans are known to follow suboptimal decision strategies, and they are very much affected by emotion, by complexity, by the context they are acting in. And therefore, we cannot assume that there will be utility maximizers, as we could do that with other robots as well. And this poses the main challenge that I'm talking here. I want to combine these humans that are not totally rational. I want to keep a long-term relationship with them. And I want them to accept automation that also has proactive behavior. So how can we leverage that proactiveness and autonomy of agents in order to understand better what this user needs and can get this behavior from these machines? So the way I'm looking at is developing an AI-based human-machine experience where we mainly need to understand how do humans and intelligent vehicles going to communicate? What is that communication about? And how we can use that communication to understand better what are real human needs. And also you need to understand that also humans might have expectations from that machine. So we need to cover this communication problem in a sense from both sides. And to do that, we propose to develop an intelligent agent that has also an adaptive HMI interface. So in particular for this particular talk, the challenge would be to develop such agent that is going to be able to learn his users' driving preferences in the automotive domain. It's going to be able to adjust its own behavior control in real time to those user needs. And doing that, he will minimize the number of manual interventions otherwise required by a user to correct that behavior that he might not like. The solution I'm going to present here will include a simulation testbed used for evaluation of our framework, the interface that I just mentioned that is a kind of novel interface in the sense that it's adaptive and intelligent, and the agent itself that learned to predict human needs and adjust its own behavior. I'm going to show also results from an evaluation we ran over 3 studies with around 94 subjects. So first of all, you can look here at this diagram just on the right side. So being an automation, a machine, What we need is that that machine is able of realizing in which system state it is and what should be the next state it is aiming to get to. If we have a model of that system behavior, whenever we know which system we are in and what is the system we would like to move to, then by applying the system model, we will know also which are the settings that we need to set in order to get from this current state to the next one. So in a case where we didn't have any users, this whole loop will maintain the behavior of the system so that it can control correctly the behavior of the vehicle, for example, a long time. But now we have the user in the loop. So whenever a user has a request from that system, for example, something is not as he would like to enter this correction. So we would need some kind of natural interface to allow that user to tell us what he wants. What we did in this work is that we also learned a model of these user preferences. So whenever the user enters his intuitive inputs, what are his current needs, we will be able to apply this model in order to translate those needs into what is the state that the user is actually willing to be in. And now we have this predicted state, we know in which system we are in, and again, by applying the system model, we will be able to move towards that predicted state. So basically, what I'm suggesting is to develop an adaptive agent that has an intuitive interface to allow people to communicate with the machine. The agent enables the logging of the data between the user and the machine. And using that data, it will be able to learn to predict the user needs and also to interpret these needs into actual system actions. The main takeaway here is that, as I see it, automation is not just about a machine, but it's a whole adaptive and user-centered experience. So let's move into the actual project and the agent that we developed. So as I said, I'm going to focus here only on driving comfort. And when it comes to how to control the vehicle, we can say, okay, where do these profiles come from, these driving profiles? So it could be either they can be calibrated by some engineer, or maybe we should be looking at human data and learn from them how this vehicle should be driven. And the reason that this is interesting is, as I mentioned before, people are human and are very different from each other. And not only they are different between themselves, that the same person can have different preferences because of some context. So the same person might be more aggressive when the weather is fine, there is light out there and the road is very smooth, but maybe the same person might get very concerned at night when it is snowing and there is a lot of traffic. So one of the questions we are asking ourselves is how we can learn what are these preferences that we understand that they are contextual. In order to do that, we ran a research project in collaboration with Bar-Ilan University, with Professor Sarit Kraus and her students, where we assumed that we could get inputs from the vehicle dynamics, driving context, and some of these user preferences through this interface. And the idea or the goal of this adaptive agent we wanted to develop was to provide the best comfort we can to that passenger or driver by being able of adjusting the driver settings in an automated way. And as I will keep along this talk, the success criteria on our side will be the number of times a user should be intervening in order to correct the driving style. So first of all, we have a simulation environment set up where we could run on these three big screens over here, a Unity-based simulation environment of a scenario that the vehicle was driving in. And then we have here some car seats where the experimenter will be sitting here and the subject will be sitting next to him with a separate tablet where he will see the intuitive interface. And what we did is we projected a video of actual San Francisco streets. We brought this content by video and we have this content being created and shown on these three screens. This map was also shown on the rightmost screen. And as you see here, we have an 8-shape route that we use for all the experiments we ran. The numbers that you see here on the map are connected to different events that we wanted to show to the driver or to have the car encounter so that the scenario is richer. So all these events could be like pedestrian crossing, a jaywalker, a traffic jam, and so forth. Okay, so first of all, let's talk about the interface. So as we mentioned, people are different from each other. And the question is how they could communicate with the vehicle. What is their concern or discomfort about a certain driving style? So for this particular simulation, as I mentioned, we use the Unity environment. So the actual behavior of the vehicle in the simulator is controlled by a set of parameters. So you see here the 10 most relevant parameters that actually affect the driving style of the vehicle. So one way to go is to explain to each of our participants what is the meaning of each one of these parameters. Let them know that each one has a slider. And whenever the participant doesn't feel comfortable, we can ask him, okay, which parameter do you want to set and how much to change the slider? But obviously, as you understand, this is not, doesn't make much sense. Obviously, while driving, you will not be expected to exactly understand which one of these parameters are making you feel discomfort. And even if you understand them, it will be very difficult for you to actually set the right value. So I separately work with a graphical designer, and we tried different concepts. And we came up with this idea of an interface where a person feeling discomfortable about the current driving style will be able to let the system understand what is bothering him without the need to say much detail about it. So what you see here is mainly this circle that represents the vehicle. So by just touching this interface, you can change its size by enlarging or decreasing the size of the circle, meaning I would like the vehicle to move faster or slower. You can also move the circle up and down if you want to say that the gap to the vehicle in front should be shorter or larger. And you can also move the circle left or right if you want to change your lane centering position. Alternatively, you can also use the slider up here. So if you move the slider mark to the right, you are telling us that you would like a more sportier driving style, and the opposite if you move it to the left. You can also notice that even with the circle or with the mark, you are not telling us exactly what is the speed you would be willing the vehicle to drive. You are just telling only the direction of the increase or decrease. And now I'm going to show you the results from the 3 experiments we ran about running this adaptive agent and how it behaved. So the first experiment was aimed particularly to collect data. We brought 30 participants to the General Motors site in Israel, and we let them drive the 8 shape I showed before, actually 4 times. But every 2 laps in that route will be initiated with the default driving style that we set up. So that we distinguish between a calm driving style from an active driving style. And we have the first 2 laps starting with either one of them, and then the last 2 will be initiated with the other one. Obviously, we balance the experiment so that different people will start differently, and also the laps were randomized. First of all, we collected in this experiment a total of 633 comments from people expressing their discomfort from the driving style. And as you can see here, because the first 2 laps and the second 2 laps had been initiated with the same driving style, you can see that at the beginning there is a very large amount of comments that are decreasing towards the second lap because we start adjusting the behavior of the vehicle. In this case, this was done by a table of rules that the experimenter could control. What you see here is the distribution of the comments, the corrections that we got from the 30 participants through the interface. So first of all, we see that all the options available in the interface were at some point used by some participant, or all of them got a number bigger than 0. And you see that the highly used option was to ask for more speed. As being in the UX team, it's not just computer science study. We also want to understand how easy it is to use or not the interface. how well it actually expresses your wish to correct the driving style. And as you see here, I am showing just 2 questions out of many other that we asked. One of them was how much the system really understood what you wanted to correct and reflected that in the behavior. And as you see, higher scores are better, and here we got an average of above 8 for that question. A second question would be how easy it was for you to use the interface, that it's novel. So here the lower scores are better, and as you see, we got around an average of around between 2 and 3 to show that the interface was easily understood and used. In the second experiment, we said we collected data so far. Let's see if we can learn what are the preferred driving styles out of that data. Instead of us giving a set of default driving behaviors, let's see if we can learn those from the human data itself. So first I will show some clustering results we got from learning these driving styles. And then I'll show further results from bringing a new set of 30 participants that now we are asking them what would be the driving style they would like to have to implement in the car, assuming they are taking a taxi kind of trip. And interestingly now, we will see a reduction of number of corrections already by doing that from 633 already to 367 comments. That is a decrease of 40% of number of corrections. So first of all, as I mentioned before, let's see how we can learn what are the preferable driving styles of people. We try all these different clustering algorithms, and what we were looking for is looking at the settings of the driving styles when a person was not giving any further comments, how we can put all these settings of those driving styles as close as possible when they are similar, and as distant as possible when they are not similar. So we want very dense clusters. And finally, we find out with the k-means algorithms, when k was equal to 3, we actually found 3 driving styles. This is not surprising. From the literature, we know that these are the driving styles people usually prefer. There is one extreme of calm driving style, and another extreme of an active driving style, and there is a normal driving style that is more or less in the average in the middle. But this time, as different from the first experiment, these numbers were learned, are results from the cluster centroids. And in the first experiment, we just calibrated ourselves. So again, we asked the same usability results. We keep getting very good scores, saying that the users recognize the effect of the corrections, and it was very easy for them to use the tablet. And now we already see that if we compare the number of comments provided in the first experiment here in orange and the second experiment in blue, you can see the drop of this number. As I mentioned, it was an average 40% decrease. So let's move in a moment to the last experiment. That's the most interesting. Just before that, I think this graph is also very interesting to note, is that in the x-axis, you have the example of the 30 participants that took the experiment, the second one. And in the y-axis, you have the number of comments each participant asked for. And as you can see, different people have different number of comments, and also even the same person with this, different people with the same number of comments could have been asking for different corrections. But you see that we have people that only gave 2 comments along the 4 trips, as long as other people were giving as much as 21 comments. So let's move to the last experiment that concludes the whole adaptive driving agent project. So here we brought a set of new 34 subjects. And now what we did is we used the data from the previous studies, and we first of all trained an agent so that he's able to predict when the user is going to be discomfort, when it's going to feel discomfort. What does it mean? The agent is able to predict if in the next 2 seconds, that participant is going to give a correction, is going to touch the interface. And we are first predicting that, but then we can say if that prediction has a very high probability, then let's try to automatically adjust the agent behavior so that we actually prevent the user from providing that comment. He will not need to touch the interface in the next 2 seconds. So first of all, we need to build that predictor. We tested different architectures for neural networks. And finally, we chose the one with the highest ACU score. And we use the convolutional neural network as it's shown here. And I will show already all the results all together. So if you remember in the first experiment where users were not given the option to choose which driving style they prefer, they were facing an experiment where the initial driving style was set up by default. We got an average of almost 21 corrections over all the set of participants. When we let the users choose what is their most preferred driving style, and also assuming that driving style was learned from data, we already see a drop to an average of 12 comments provided by these users. And now when we use our adaptive agent, we see a drop of only 7 comments on average. What we see here is that in the background, the agent was predicting that corrections will be asked for, and he will automatically correcting its own behavior even before the user had to tell about that correction. So there were many, many corrections, like 19 overall on average, that the agent was performing. But still the agent is not 100% accurate. So these 7 comments on average could have been the result of either the agent not predicting correctly that the user wanted to change a behavior, or that the agent predicted correctly, but his correction was not the one that the user wanted to be done. But still, you can see the drop from 21 on average to a 7.4 on average. So just to end this part of my talk, the main contributions of this project is first that we provided another way of looking at the interface, how people could enter their inputs and needs to a vehicle in a more intuitive way. We were able to classify driving styles following human data and preference. We were able to learn a predictor for when a user is about to provide a correction. And also in real time, we were able to automatically adjust the driving behavior so that human acceptance is increased. So we showed that by reducing the number of manual interventions required and increasing driving comfort. Just to conclude, I think machines are great at executing actions, and humans, our users, have needs and preferences, and we need to invest into how this communication problem can be bridged, how this gap can be bridged, and not trying to develop machines that are doing what humans are supposed to do, or humans trying to understand these machines or adapt themselves to them, but the opposite, I think, is the way to go. And I will be happy if there is still time for questions, and if not, I will still be at the end of the webinar to get more questions. Thank you.
Okay, so thank you very much. There were no questions asked in the Q&A interface. So please, Claudia, I give you now the opportunity to introduce the next speaker.
Okay, great. So as I said, I will be until the end, obviously. So if anyone wants to ask anything or send me email,
yes, they're going to be here past 6 o'clock a little bit, so it's more.
Okay. And now let's move to the other talk. We are very glad to have here to host Danny Atsmon from Cognata. Danny is a very active entrepreneur in the automotive domain. Currently, he's the founder and CEO of Cognata. That is a company that combines artificial intelligence, deep learning, and computer vision to simulate testing for automated cars. He has previously been the Harman's director for ADAS and director of machine learning. And we were happy to have you here, and you can start. Thank you.
Thank you, Claudia. I'm going to talk about the technology that we have developed, which is called Real-to-Sim. As Claudia mentioned, Cognata is developing simulation. We're like, from Rehovot in Israel, near Atsmon Institute. And the real-to-sim technology is coming to solve the following issue that we have in simulation platform up until now. It's about finding the relevant, realistic models. Like the idea with simulation is to bring into the simulation the relevant sensor models from real life, actual traffic models, and interesting edge case scenarios, and then to run them with scale. So with real-to-sim, we're bringing the real world into the simulation for the purposes of validation and training ADAS and autonomous vehicles systems. Now, in a very brief, like about Cognata, we were founded 4.5 years ago. We're now more than 50 employees, which coming, from very respectable companies that, you might recognize from that nice list. We raised more than $23 million from top-tier investors, and we have many top-tier or tier ones partners that are distributing our software and help us navigate this world. So let's go to the problem itself. So validation for ADAS and autonomous driving, it's a problem that increases in each cycle of this industry. When this cycle started with level 0 system, it's just like warning system. You need to drive thousands of kilometers to validate it. Today, we're talking about level 2 system that has control over both steering and gas brakes. You need more than 1 million miles to validate a platform. And when you're going in the future into level 4, we're talking about billions of miles to validate that your system is working correctly to reach the level of a human driver. Now, in terms of how we tackle that in Cognata, just in a brief explanation, we have 3 types of solutions. Simulation, which it's a playground that replaces real-world driving. You connect your platform into the simulation and have all the sensors that you have in real life and similar actuators that you have in real life. And then you can drive it, whether on a single PC or in a hardware-in-the-loop solution. We are supporting all the known standards coming from the Assam, like Open Drive and Open Scenario. So simulation is one thing. Datasets, it's actually activating our simulation for our partners. Some of the companies tells us, we don't want a very complex simulation platform. We want you to create for us, for example, traffic signs data sets, or pedestrians with all kind of positions, or traffic lights from all over the world. Just get us these millions of samples instead of us going out there and annotate. And we're doing it as a service. The third type of solution that Cognata is delivering is validation services, meaning that we are taking end-to-end with the OEM, meaning that we are taking data which was actually recorded from the vehicle, ingest it automatically, kind of auto-labeling the data, ground-truthing it, and then provide large-scale validation for the platform that we are testing. In terms of how it's distributed, we have 3 types of solution. A local station, it's Cognata, which is installed on a PC locally, and you can drive hundreds of miles per day on that. Going from that, we have cloud and services, where you can drive billions of miles. And at the end, we have hardware in the loop bench. It's actually connecting Cognata to the selected embedded system and testing that the actual rig, the actual sensors, the actual actuators. In terms of technology, we have 4 layers of technology: static, dynamic, sensing, and cloud. On the static layer, we're building 3D cities, full cities in 3D, based on off-the-shelf maps, like GIS layers for buildings, elevation maps for topography, high-definition maps for navigation, and satellite imagery, where we apply computer vision upon it to furnish the scene with all the small details that you have in real life. The end result is that you create a digital twin of real life. In a few minutes in our cloud, this is my office to the left. So if you cannot visit me due to COVID, you have it now virtually, and we created with that technology digital twins of San Francisco and Munich and Shanghai and other places in the world. So that's the first deck. Now, when we create that, we are creating a digital twin, but it's an empty world, meaning there's no moving objects, no like pedestrians or like vehicles out there. And when we are adding the dynamic layer, adding the actual vehicles and pedestrians, we want it to be geolocal. Meaning geolocal means that we would like to add the drivers of San Francisco to San Francisco and Tel Aviv to Tel Aviv. We would like it to be very specific or an actual digital twin of the area that we have modeled previously. So in order to achieve that, we're using data streams from traffic cameras and apply on that computer vision. So you can see here the actual vehicle detections on the left, and to the right is when we put it on a bird's eye view, so you can like, snap to a lane. And the idea is that not only we are getting, the routes of the vehicles, more interestingly, to kind of like characterize how people drive in different locations, we are like calculating the time to collision that they are keeping, the attack angles when they're switching lanes, how different classes react to each other, for example, how a bus reacts to a vehicle, to a truck, or to a bicycle. And with that, it's just learning how people drive. Now, when we would like to actually use it, so we are learning the data using reinforcement learning. And when we put it into our simulation, this is like a simple simulation of what we call semantic simulation. What you're seeing here is a simulation of 3 lanes merging into 2. Now, this is not a replay. Each of the drivers here has its own AI, and the vehicles would stop or like, stop and overtake or like just overtake when they're seeing an obstacle. And it looks realistic because it's derived from actual data. And the nice thing about it is that when we run it with scale, with like billions of like running, we're getting all the familiar edge cases that arises from real life. So again, bringing the traffic into the scene. A learned model. The third part is about the sensors. So in Cognata, we are modeling all the sensors that are out there, like LiDARs, cameras, radars. And the way that we do it again, like bringing the real world into the scene, as I said. So we're using here like learned models. So I'll just show it like in 2 examples. The first one is about camera model. So here you're seeing like real video. It's taken from like the Kitty data set. On the left-hand side, synthetic implementation of the same scene. It's not Cognata, it's called the virtual Kitty. It's an open data set as well, and you can see it doesn't look realistic, not the sky or the vehicles or like the vegetation. In the middle is Cognata. It's what we call deep neural network inspired sensor. We learned in offline how the sensor behave, how to do transfer laning between the synthetic data and the real data. And the end result is that we're doing real-time rendering with our deep neural network of the scene, and we get a video image that looks exactly like the real video, or like very, very close to that. And we showed that, mathematically it works. And we're doing the same stuff also for LiDARs. This is like our collaboration with another Israeli company, with Innoviz. So you can see here like nice rendering of the scene from the simulation. And here on top of that, our rendering of like a LiDAR from Innoviz, and the 2 of them together. Again, instead of like driving millions of miles, you can just do it in the scene. And of course, the whole thing is running on every public cloud, on GCP, on Amazon, and on Azure, of course, and creating like thousands of permutations easily. So this is the platform, and now, sorry. Now let's talk about validation challenges. Like this, like the the challenges that we are trying to solve as a company. So we have identified two challenges. The first one is on perception. We talk mainly about low light conditions, glare. This is for the perception stacks. And prediction and control, it's about finding the dangerous scenarios. So driving outside, it's something that you must do when you test like an ADAS system. But the idea and what I will like demonstrate here is how you bring the relevant part into the simulation, how you pick that, how you sift it and find the interesting stuff. So I'll start with perception. Perception is critical. Most of the recalls in the advanced driver assistant world, in the ADAS world, were coming from perception, like the big ones, like from radars, from cameras, of like not detecting or like no false positives, and that like initiated an AEB. And like when you have a recall, it's a huge event. It's like, it's an event of like $500 million at least, if not more. So perception is fundamental, and it's like the main tool that we use as humans. And the thing with perception is that it learns from experience, like from the massive amounts of interesting data that might occur or not occur in real life. And for example, like a sofa on the road, or like a plastic bag, whether it's a plastic bag or like something else, whether I can drive it through, or like, or should I like avoid it? And the proof is that in real life, your possibility of finding those interesting scenarios is close to zero. Like this is the distribution that I took from the Lyft, the Lyft autonomous vehicle dataset. And they gave like the distribution of objects. So you can see that you have like most of the data is cars. If you want to see pedestrians, it's almost an order of magnitude from the pedestrian to the cars. And if you would like to get like a very rare event that you would actually learn from it, it's, on the very, very long tail. You almost would not see it. And if you take, this is a graph from the industry, it means that when driving along, and driving along is very, very expensive in terms of like costs, only even less than 1% of the data that you took in real life survives for the training and validation, meaning that 99% of the data that you have collected is meaningless. And now I will explain a little bit about the concept of synthetic data. So we understood that, perception is critical, but also like driving outside would not be an answer. It would be, something that would really hard to define quantitatively how to find the interesting part. So let's talk about synthetic data. Is the data that we're producing from the simulation as realistic as possible versus real data. So let's talk about the difference between those. So synthetic data has perfect labeling versus prone to errors, relabeling. It can go from different time of days, geographies easily, whether like in real life it's limited to like where you've recorded. You have unlimited scale like in the cloud, where like in real life you're limited to where you drive. The representation of the sensor is a representation. As good as we do it, it's still a representation, while in real life it's true. It's like the actual. But the actual sensor placement is expandable, and you can change it, and you can bring edge cases with scale, and the cost is like a friction. So what did we do with Cognata? We have created, like, in order to, how to find this 1% and extend it, how to make more of it. So what did we do is like a pipeline that ingests real life data, analyzes the data, find all the object distributions like in the Lyft, and then generates the complementary part, meaning instead of having, these pedestrians as 1 to 10 occurrences, or this sofa in 1 to 10, we will bring many, many cases that will make your perception stack more, kind of like generalized among them. And when we're doing that, the idea is that not only you find the interesting stuff, but you can have answers. So Cognata today has, hundreds of thousands of miles of synthetic environment, which are very realistic, from full cities to highway driving to parking lots and other places, off-road experiences as well. We have like huge object catalogs of all the traffic signs in the world, all the traffic lights, all the like the vehicle models, etc. And the sensors, like, all the sensors with all the possible ground truth you can think about. So for perception, I think the message is clear and how you are actually solving and bringing coverage to this problem. Now, the second part that we would like to talk about is how you find like interesting scenarios. So first of all, I will show some abilities of Cognata. And it shows a video that we took. And this is how we brought it into the simulation. So you can see like one-to-one representation of all the vehicles. So we kind of acquired them with computer vision here. And here we put them into the sim. And the idea is that with that, first of all, we can do the ingestion of like finding the interesting stuff. The second stuff is we can find the interesting scenarios from real life and bring it to the simulation with like high level of details. And when we are doing that, we can take the real life scenario and add permutation. So I took a very simple scenario of a car which does a cut-in into my lane. So from the left to the right, and this is like the ego vehicle. Now, I took this log and played with the parameters. So one time, the ego vehicle, my vehicle, went in 10 meters per second versus like the vehicle target was in 22. So the cut-in would be, very far, and I will have enough time to stop or like change lane. The second incident is when the ego vehicle is driving in 20 and the vehicle target in 22. So the cut-in is closer, but I still have enough time to react. And the third part, yes.
You have less than 5 minutes, okay?
Okay, so I have like one slide more. I will just finish that and then I will go to Q&A. And the last part is like 20 ego and like the GVT in 21 would be a dangerous scenario. Let's see them all running in parallel. So again, from safe to moderate to hazardous. And you can see here the cut-in is like ended. And here we like switch lanes to avoid an accident. So this is like just taking one log and making something interesting from it. And that's it. So synthetic data is accurate, diverse, and more interesting, it's tailored solution to the problem that is being brought up. And if you have more questions, you can just shoot me an email. And that's it. Thank you. Any questions?
So I don't see any questions right now, but Shai is publishing the mail. So anybody that would like to contact you later can do it. Just a second, one question is how accurate the mapping from measurement to simulation?
Mm-hmm. So in terms of like static layer, like how we build cities, we're working with partners that are like using gliders to do like the scanning. Their like equipment is in urban areas, it's between 2 to 5 centimeters accurate, and in highways 10 centimeters. It's like a very close representation of real life.
I will pick up from here. Thank you very much. Thank you. It was very nice. It is my great pleasure now to introduce Professor Dov Levine from the Technion Physics Department. He's going to make a presentation about how a physicist looks at traffic. And the reason Dov, are you in, please? And the reason Dov is here is because he has written a paper with Beham and Middleton, which became the BML traffic model. And this paper has over 1,000 citations, and it became a classic in the field. So he's optimally suited for this. Dov, please come on. And there is one more thing that that I have to tell you about Dov Levine. He is also the guy who invented the name quasi-crystals for the type of materials that Danny Shechtman has gotten the Nobel Prize for. Thank you very much, Dov. Please go ahead.
Okay, so so my talk is going to be rather in antithesis to the previous two talks, you know, I was telling Freddie that I thought that basically I'm the entertainment portion of the program. So let me start with a joke, and the joke is, it's not funny, but it is illustrative. A farmer has a bunch of cows, and the amount of milk which he's producing is not very satisfactory. So he calls a psychologist, an engineer, and a physicist to give him some advice and help him solve the problem. So the psychologist says, well, yeah, the cows aren't very happy because when they go outside, there aren't flowers and they don't graze in a very conducive atmosphere. So what you have to do is you have to change their grazing, and all will be better. And so the farmer says, okay, thank you very much. Goes to the engineer. The engineer says, well, the milking machines are not really very efficient, and so you're just losing a lot of production because of that. But I can design new milking machines for you. And then he goes to the theoretical physicist, who says, well, I know how to solve that problem, and the only thing I need to assume is a spherical cow. So this is the spherical cow joke, which is fairly well known among physicists. And so here's just a cartoon of the same thing. You assume a spherical cow of uniform density while ignoring the effects of gravity in a vacuum, and the cow gets less and less pleased. But the point of this joke, although it's a questionable humor, is that physicists tend to abstract problems. So here's the bait and switch of this talk. You thought you were going to hear a talk about traffic, maybe, and I suppose I'll touch upon it. But the bait and switch is, I'm going to tell you a little bit about phase transitions first. So you do know about phase transitions, at least in a colloquial way, because you all know that water has three phases. There's solid phase, which is ice. There's liquid phase, which is what you drink, and there's a gas phase, which is vapor. And a diagram such as I'm showing here is called a phase diagram. On the vertical axis is pressure, on the horizontal axis is temperature. 1 atmosphere is about our ambient temperature, at which ice melts at 0 degrees and water boils at 100 degrees. So the point is that I have 3 phases, and the 3 phases transform one to another at so-called phase transitions. Now, systems such as traffic are much more complicated than systems like that I'm showing right now, because they're systems which are out of equilibrium. But I don't want to get too deep into the details here. But I'll give you one sense in which how we abstract problems, and that's the way we look at magnets. So when we look at a magnet, we take a lattice, which is a set of squares, one next to another, and inside each square we put a spin. The spin is either up or down. I've colored them blue or red for no particular reason. So plus or minus 1, if you like. There's an energy associated with 2 adjacent spins being both up or both down, or one being up and one being down. And this for us is an abstraction of what a magnet is, and gives us information about how magnets will behave if we change temperatures. So for example, if we want to see how strong a magnet is, that's given by what's called the magnetization. It's the net difference between the number of spins pointing up and the number of spins pointing down. As you change the temperature, that changes. In particular, if you're at very low temperatures, you have the magnet is stronger. and at higher temperatures, the magnet becomes weaker, and in fact, above a certain temperature, which is called the critical temperature, it's not magnetized at all. That's an example of a phase transition from magnetized to non-magnetized, and it's also it has similarities, in fact, to the previous water example I gave, but that's in the advanced course. If you look at the way the system develops, so what I'm showing here is a zoom out of a system such as I showed you a slide or two ago, where red is spin up and blue is spin down, or vice versa. If you look at the bottom, when the temperature is high, you have equal amounts of blue and red. That is to say, there's no magnetization because the net difference of the number of up and down spins is effectively zero. And if you're at low temperatures, which is the top panel, then you see there's a preponderance of, let's say, up spins, and the system is magnetized. Okay. The point is, for us, that the same thing happens for other lattices. So I showed you a picture of what we call a square lattice, a lattice of squares adjacent to another, and put spins in each square. But in fact, you can look at other lattices as well, such as a lattice of triangles, a triangular lattice on the left, or one which is a little bit more complicated, which is called Cognata lattice on the right. And if you put spins inside each of these shapes, the triangles, or let's say the hexagons, and you use the same energy as we did before, you'll get the same results. That is to say that these small scale details don't matter. And this is what we call universality. And this is what physicists always look for. We always look for universal features. And these manifest themselves if they don't show up, if they're not dependent on small scale details, then they manifest themselves on in large scale phenomena. So essentially, we as physicists are interested in large scale phenomena, and not in the absolute small scale details. So here's the BL-MAIL model, which Freddie mentioned a couple minutes ago, and it's a real abstraction of traffic flow. So how do we abstract traffic? So the way we abstracted a magnet is we said we have guys pointing up and guys pointing down, and there's some interaction between them, and we watched it go. So we want to do something similar. And so what we clearly need if we want to talk about traffic is cars. So we'll have cars. We need a space. So I'll take as my space a square lattice again. And we need something to regulate the traffic, which we can take to be a traffic light. And in this particular model, which is about the simplest one you can imagine, cars either can go down or they can go to the right. They can't change directions. A blue car always goes down and will from the beginning of time to the end of time, and a red car will always go to the right similarly. I'm going to put cars down randomly on the space, and we'll have a traffic light regulating the traffic, and the traffic light will tell all the blue cars that they can go down, let's say, and all the red cars that they can go to the right, and they have to take turns. And the point is that when the traffic light is green for the blue cars, then every blue car which can go down one position will do so. And what I mean by can move down is that it's not currently obscured. It's not blocked by another car, either another blue car or a red car. After all blue cars have gone down, all red cars will go, and they have the same restriction. If they're not obstructed, then they'll move forward one step. Okay. What happens when they get to the end? When they get to the end, they come back into the other side. So this model lives on a torus, if you like. So a blue car or I should say a red car which goes to the right, like the one in the upper right-hand corner, if it moves, it's going to enter into the top left corner. And the blue car in the second column, bottom row, is going to advance going down, and it's going to show up at the top row. So, for example, this is going to look like this. Okay, and first the blue cars went down. Now the reds do. Blue, red, blue, red, blue, red, blue, red. So you don't really see very much if the system is so small. But let me now look at a system which is larger, and let me look at various densities of cars. So what we'll put down is roughly equal numbers of blue and red, and the total density, which is the sum of the densities of the blue and the red, is going to be written at the bottom of the slide. So here we have 1% filling. So 99% of the space is unoccupied, and we'll just watch what happens. So the cars just drive, and basically nothing happens. It's not very interesting, right? Everybody goes, everybody's happy, and there's not a whole lot of things going on. Okay, let's make it a little bit more crowded. This is 5%. At 5%, again, things are moving along quite nicely. If you have sharp eyes, then you might have noticed that there was some bit of organization. But if not, you'll see it in a moment. In this case, you'll see it much more clearly. This is 10% occupancy, about 5% red, 5% blue. Start in a random configuration, let these guys go, and now you can see that the system has organized itself rather nicely into lines at 45 degrees. And you can also see that that it seems like all the cars are moving, which is in fact the case. Let's look a little bit. The higher density, this is 20%, and once again, you have these characteristic lines at 45 degrees. But you can also see that at every time step, pretty much everybody is moving, and in fact, if you wait long enough, everybody will be moving at every time step. And that's sort of and so here's one more, 0.3, and the same thing is going to be true of this, although you can see that that it starts off by organizing. It takes a while before it organizes, so you have these funny flame-like structures. But if you wait long enough, you'll get to a point where every blue car will move at every time step, and every red car will move at every time step. Nobody will obstruct anybody. That's a pretty remarkable thing. It's called self-organization. We didn't put that into this model, right? The model is exactly what I told you what it was, but these dynamics lead to an organized structure, or organized structures, I should say, because there are many, many of them, such that nobody ever obstructs anybody. If you wait long enough, you have to get through the initial transient. So that's pretty much where we are over here. But as I say, that's the most remarkable thing about this model, is that everything self-organizes. It's like you have a set of gears, and the gears start off in some sort of a random juxtaposition, and you run them together, and all of a sudden everything begins to mesh properly and just by itself. If you look at higher density, so this is 0.33, this is a third, 33%. Those same characteristic fiery-like structures or erosion structures show up. And now you can see that you have another, you have two distinct directions. And now you can see that you begin to form some sort of some jam structures which decay, they break up. So we're not gonna keep going at 0.33. So let me look at something even higher. So things look initially the same. And you have those jam structures forming. And eventually, this simulation will end. And when it does, you'll see that there's no motion at all. So this is now the system has completely jammed. So the phase transition went between a phase where everybody was moving with perfect efficiency to one where nobody's moving whatsoever asymptotically as if you wait long enough. That occurs at around 33%. So what we have here is again at this higher density, things begin to move, and then they end up in a jam. And the one point I want to make about this jam, as about the previous one, is that it's a single jam, because this is wrapped on a torus. This is a single jam, that is to say, or will become a single jam, I should say, in a second, because all of these, this long jam at 45 degrees, in fact, because of the periodic boundary conditions, the fact that it lives in a torus, is a single jam, and there's a continuous path between any two cars on that on this. Okay, so that's an example of a phase transition, and here's how this is the parameter which distinguishes the phase transition. This is from this original paper that we wrote quite a long time ago now, and the y-axis, the vertical axis, is the average velocity. It's the success frequency, if you like, or as you as you're trying to move. So 1 means that everything moves at every step. 0 means that they're completely jammed. And so you can see that at some density, which is written p here on the x-axis, you have a sudden drop from perfect motion at the largest size system that we were able to simulate in quite a long time ago now. Of course, these are tiny systems nowadays, but you see that there's a transition from perfect motion to perfect jamming. This I don't need. And the question is that all? Or one question you might ask, is that all? So let me just show you what happens if you look a little bit higher. If you look a little higher in density, you get, again, these initial clusters form, and then they're unstable and they break up. And in this case, it's about to end. And what you can see now is that while before there was a single jam, now you have 2 jams. It's like bracelets encircling a torus, if you like. And now you have 2 of them. So there are 2 jams here, or 2 lines of jams. And if you go higher, which I won't do, you'll see more, because you need rather large systems to see that. And if you go, sorry, that was not the right way to do it. There we go. If you look higher still, considerably higher still, then you no longer have that structure at all. So the point is that you go from a flowing state to a jam state to something where these jams permeate the entire space. So that's that particular model, the BML model, which Freddie wanted me to talk about. But there are other ways that we think about such problems as well. So here's an example. So in high school, you or maybe after that, if you studied physics, you learned about gases. And here's an example of an ideal gas. Actually, there are 2 of them, one to the left, one to the right. They're going to eventually mix. But the point is, you can think about these as being steel balls which are colliding one with another, and you get complete chaos. Okay. Now, if we look at a model which is very current right now in physics, called this is called active matter, and this is a field of extreme interest in non-equilibrium statistical physics. There's a model called active Brownian particles, and these particles, unlike the gas I showed you a second ago, have their own source of energy. They have a battery, and they move with a constant velocity. Unless they encounter other particles, then they veer out of the way because they don't want to crash. They don't want to overlap, and they go straight. But occasionally they change directions in a stochastic fashion. So if you look at what happens to them now, and you compare it to what you saw with that gas I showed you before, you'll see that you get the formation of clusters. And so this is sort of like traffic jams, if you like. Of course, there aren't any roads here. But this is the essence of, for us, of what jamming is. You've got particles which move. They have some sort of interaction. The interaction is repulsive, by the way. They don't want to be close to one another, but they are anyway. So, and this exists, by the way, just as long as I'm making a pitch for physics, you can do experiments on this, and this was done in the group of Paul Chaikin at NYU. You take tiny micron-sized particles which move through photocatalytic decomposition of hydrogen peroxide.
I hate
when
to do this,
you
dog,
shine light on them.
I hate to
Yeah, I
do
just want to say, yep.
Okay.
Yep. Shine light on them, they cluster, and when you turn the light off, all the clusters break up. Okay. We've been also looking with postdoc Matthias Kasulis and another faculty member at the Technion, Daniel Hexner. We've been looking at a variety of models where cars will try to avoid one another, and we find all sorts of features which appear to be independent of the details, such as the lifetime of cars trying to find their way to their destinations. So okay, so let me just conclude. What we look for as physicists is common features in different systems. To do that, we particularly are interested in large-scale phenomena, the correlations over large distances, and we look at different phases and their transitions between them, where phases represent different types of behavior. And we use abstract models which, when we're successful, will retain the essential features, so we won't throw the baby out with the bathwater, and we'll throw out everything else, which is an essential for our purposes. And that is all I have to tell you today. Thank you very much.
Thank you very much, Dov. It was very exciting and interesting. And next, we are going to go from traffic to the individual vehicle. And Boaz Mizrachi is going to tell us all about the tactile sensing that is the missing sense in smart vehicles. And Boaz is an entrepreneur. He has in the past he has been the founder of a very famous internet routing company called Charlotte's Web, and now he is the CTO of Tactile Mobility, a company that is equipping modern cars with tactile sensing. So Boaz, Dr. Boaz Mizrachi will give us the talk about tactile sensing in the smart cars of the future. Thank you, Boaz. Please, the forum is yours.
Thank you, Freddie. I hope you can see my screen and presentation.
Yeah.
Thank you. So first of all, the title is not PhD, as I didn't conclude my PhD with Professor Sidi. But anyway, I would like to start speaking about a problem we have today with the smart vehicles. It's the sensing. And as you know, probably most of the sensors today are based on visual, line of sight, like LiDARs, radars, camera, infrared, etc. It's all pixels. But let's start with a question. Can you drive a car with visual sensors only? So if you try to think about it, imagine yourself controlling remotely a car equipped with any type of pixel sensor you want, like 360 around it. And in your office, you'll have screens around you relaying the information, the visual information with zero delay, let's say. And you have, like in a video game, you have a steering wheel and pedals. Will you dare to drive this car remotely? Especially if it's a car you don't know of before, it's the first time you drive it remotely, unknown places and roads, not the most sunny day, and you have people you care about sitting in the rear seat. So I guess the answer will be no, and it's mainly because the visual information is not enough. Maybe it's 90%, maybe 99%, but it's never 100%. So what is missing? And if you try to think about it, what you would like to do is something with your hands, like feel the road, feel the surface, feel the car and the interaction between them. And this is what this company is about, tactile mobility. And I will talk about this missing sense, how we represent it, how we handle it, and then a little bit talk about our recent activities in the company, which is going to production, start of production next year with BMW. So in a nutshell, the company is a software company where we have two parts of the software. One is what we call a tactile processor. It's a software. It's a very compressed one, like starting from 200 kilobyte. We can even go lower than that. With lean resources of CPU time and RAM memory and other types of resources. It is located inside the ECU. Normally it's the chassis ECU or stability ECU in the car. It collects all the existing hardware sensor data in the car, like wheel speed, torque, engine torque, accelerations of different types, etc., gear position, etc. And then out of that, close to real time, it derives what we call virtual sensors related to tactile sensings of the road and tactile sensings of the vehicle itself. This virtual sensor information is then provided back to the network system in the car. So the other ECUs, other application softwares that are steering, driving, and controlling the car can use it normally for precondition. And then in parallel, in addition, when allowed, this virtual sensor information also transmitted to the cloud. In the cloud, we have the second part of the software, which we call the tactile cloud. And there we generate or map two types of things. One is what we call the vehicle DNA, and it has to do with the what is well known in the industry as the digital twin of the car. Think of that like a physical, mathematical, machine learning model of a specific car at a specific time, mainly describing the performance of the car in terms of dynamic handling, but not just. And the second part is what we call the surface DNA, which has to do with attributes of the surface, things you can feel rather than see, like road grades, inclination, like road roughness, friction coefficient, and this will be the example I will show you in a moment. The next slide is like the full picture of what you can do with that. So think about the first guy who introduced a camera to the car as a sensor, okay? And today it's common knowledge that you can do a lot of things with that sensor, okay? You can look outside and see cars, you can look inside if the driver is asleep, you can look out into the sky, see if it's raining, etc. So we are now introducing the first tactile sensor into the car. And out of these sensors, we are generating or enabling a lot of applications. So the inner circle, as you can see here, with the darkest blue, stands for the virtual sensor we can provide in the car during driving to the rest of the ECUs. And some of them has to do with the surface DNA, like the grip or friction coefficient, surface events or distresses, and I'll show that an example in a moment. Roughness index, aquaplaning indication, and things that has to do with the vehicle DNA, which has to do with the vehicle health and the tire health. And also, in case where we are allowed and it is needed, we provide about a driver profile. Then the outer rings here are describing what we provide to the cloud side from time to time. By the way, very compressed and dense bits and bytes. We are talking about less than 100 bytes per kilometer. And according to that, we can derive back to the vehicles like a horizon indication ahead of the car, normally regarding the surface conditions, which is very important for the autonomous cars, but also for today's cars to get alerts and precondition the car accordingly. And the outer circle stands for all the nice monetization channel we can do with the data once it is generated in the cloud side. Here, since time is short, I will not go into all the details, but you can see here examples of surface DNA elements, okay, information that we generate inside using this edge computing in the car, and what you can do with that on the cloud sides and what are the potential customers. For example, you can map the pavement and surface quality, which is different than what you would map with a visual sensor like a camera. And this information is generated into layers of pavement that can be used by, for example, road authorities and municipalities. And accordingly, you can prioritize maintenance, yearly maintenance, and stuff like this. The next slide shows a little bit of the virtual sensors that has to do with the vehicle DNA. So you can see different types of them. For example, tire health. Today, in most of the cars and new cars, you have an indication of tire pressure monitor system, TPMS, which indicates if you need to inflate your tires. But you don't have today, for example, a virtual sensor specifying that you need to replace the tires since the tread depth is too shallow, or the tire is stiff or old or worn out, okay? So this is additional virtual sensor. By the way, as all the other sensors is software-based only, where you can provide close to the incident an indication that something happened to your tire. The next slide is a little bit drilled down about our architecture or processing concept. And for this example, I used the surface DNA processing pipe, starting from real sensors in the cars mentioned like wheel speed, throttle position, steering angle, etc. And then the inner stages inside the vehicle are the first stage is the signal processing. And then on top of that, we apply very compressed machine learning and out of that, we filter that out and generate these micro events. So you can think of them like pixels with the common video language. So for the tactile language, these micro events are our pixels. If you construct later on these pixels, you can do that in the car, but nobody will do that on the cloud side. You will get what we call words, which are composition of these small events or letters that stands for phenomena on the road, a specific phenomena. So for example, a specific bump is different from another bump because it is composed of different types of letters describing it. And then eventually you can see on the right side outcomes like visual map layers of indications you can get there. Here is a little short video showing how it looks like. So we'll show now a vehicle driving on a pavement, and some of the signals that are collected and detected, only some of them, out of which we can derive the small events on the surface. So you can see these small scratches on the pavement, what's called like a crocodile skin of the surface, and routing, etc. So it can all be detected with the right quality and with the hazard level that needs to be maintained. So next slide is an example of output. This is a pilot that we have completed now with municipality of Haifa, so you can identify your map, your city map. So what you can see here are several different types of layers that we have generated, like for example pavement scoring. There is a standard called PACER, which we showed compliance to that, pothole detection, alerts, etc. This was collected by a fleet of around 20 vehicles. These vehicles belong to the municipality, driven by people who work in the municipality, roaming around the city, for example, giving you reports. And these guys have an aftermarket device using our software, embedded software, and it is transmitting to our cloud and generating these nice maps. A little bit what's happening in the company recently for the past years, regardless or along with the COVID that we all experience, we have nice progress in the company. We have a Porsche company invested now in Tactile Mobility, our partners. We have partnered with HERE, the mapping company, as an interface to our customers. And then maybe the major thing that we're working out these days is the start of production of Tactile inside of a unique tactile processor software within BMW car, like the entire series, and the start of production is expected to be in July coming year. This will be the first time to have an embedded software company inside a real ECU for all these cars. I mentioned collecting data from real sensors in the car, while the main application or main virtual sensor that will be provided will be the available grip level or the friction coefficient. And you can imagine yourself like a few tens of applications or software inside the car that are using this information, this very important information, for preconditioning. For example, if we detect that the road is frozen, for example, then you would like to keep a longer distance using adaptive cruise control in front with the car in front of you. So in the next few slides, I would like to share with you, mainly with pictures and a little bit with stories, how is it to work with a company like BMW as a tier one with this company, providing a software, working with these guys. and reaching start of production in like 7 months from now. It all started around 3 years ago, maybe a little bit more, where a scouting agent from BMW startup garage approached Tactile Mobility, and they described over a phone call a problem they are now trying to solve. So they told me, like, imagine yourself a highly autonomous vehicle driving on 2021 at the 250 kph, and the driving is sleep. So I told them, good luck for you and for the driver, but how can we help you? So they said that a very important condition, which is not sufficient but important for that, is to know what is the available grip level of my tires with the surface, like 300 ahead of the car. And so this is how we started. And then we gave a proposal for that, how to do it, like collecting the information from ECU while the car is driving, generating a quick and refreshed map on top of that, and then providing this information back. So you have like a horizon prediction of the surface in front of you. This is how it started. On the right side, what you can see here is our aftermarket device, which normally we use today for pilots and early products. The next stage was to work and prepare a POC with the BMW near Munich in Aschheim in the proving ground. For that, we got a BMW 335, 300 horsepower, and the target was to detect the mu, the friction coefficient of the surface while driving on it at cruise, like 80 kph. And for that, they have proving ground with different types of surfaces, emulating ice, for example, emulating low mu, high mu, etc. And that's what we need to show, like while cruising on top of that, our aftermarket device, collecting the information, analyzing it, close to real time, like 1 second of delay, detecting that we now entered an emulating ice surface. It was a very successful POC. It took us like 1 or 2 weeks to complete the integration and calibrate the car to show it. And following that, they were so happy, the guys in BMW, that we set aside after the successful experiment, and just like a movies, we took a small paper, and by handwriting, we wrote entirely what's today we are realizing with these guys. So this is the actual handwriting that I did there. Then we got a second car, was BMW 750xi. That's the highest level of cars there. The longest one, the heaviest one. You can see me driving there, and one of our engineers sitting behind nicely. So we took that car again for like 2 weeks, calibrated, and show again the same magic on a proving ground. Next is the toughest place. This is Lapland, north of Sweden, where every OEM has its own frozen lake, normally closed for outside passengers, where they do the winter campaign, as they call it, the winter tasting. And normally around January or February, there is a visit of the CTO of each company, or the R&D manager who goes there, who see like for 2 days all the presentations, all the demo. He drives the car himself, also competitors' cars, and then decide after 10 minutes of driving and experiments that if he wants this application or for production or not. So you can see here a frozen lake on the left side, and the car we're driving on, You can see here the houses that you rent and drive. By the way, all the cars are test cars, so they are covered with these stickers just to, people will not see the exact structure of the car. And then in parallel, we went through RFQ of the 3 rounds with the major tier 1s, and we won it. And continued calibrating and developing our software with different types of cars there. Here I can show you a different car doing an experiment with aftermarket device. What you will see here, it's a proving ground near the frozen lake, where you have a pavement which is heated asphalt. You will see it in a moment. And you need to detect that you are driving from a low mu of a frozen road into a high mu of defrost asphalt, and detect it close to real time. This is something that couldn't be done so far in the world, like by cruising. And this is the new thing that, one of the new things that this tactile processor can provide. Let's see the movie. So you can see the graph in a moment of the friction coefficient. You can see it here, it's a low mu, like 0.2, 0.3 mu. Then you can see here on the horizon, we see the pavement, the heated asphalt. By the way, it's -20 or -30 degrees outside. So now we can detect a higher mu. You will see the graph on our screen jumping up with a little bit delay, and then going back driving on low mu, so you can see it decreasing. And then we completed this test. So this was a different car, different OEM, but also very successful. Yeah. Next slide, close to the final one. So integration, it's what we're doing these days. Sometimes we get other types of sensors, like what you see here on the left side. By the way, this is a different OEM, another OEM. These are Marvis sensors installed behind, like laser readers of the surface, detecting if it's frozen or not. Most of the software is written by the OEM using MATLAB Simulink, as you can see here. However, we are doing it for the first time. We are writing a C code in some assembler and providing our tactile processor to be integrated with their MATLAB Simulink. It's all based on AutoSAR software stack, so it can be ported from a car to another later on. On the right side, you see a famous church in Arjeplog. This is the center where all the car OEMs in Europe are doing their tests, and this is our traditional picture there at the end of a successful POC. So these days, we are very close to the code freeze. Like almost daily, providing software releases for BMW to check in the proving ground. Unfortunately, these days, due to the COVID, we are not very welcome there. So we do it remotely. And the first car that out of the BMW entire product line that should hold our software inside will be the iNext, as you see in the picture, in a few months from now. So
Thank you.
I think that's it. Yeah.
Yeah, so we are about to start our last talk. It's going to be given by Dr. Roy Sasson. He's the current head of product analytics group at Waze in Google. And also he's a lecturer at Tel Aviv University and the IDC Herzliya. I think I'll let you talk so we have a full talk and we can enjoy it. Thank you.
Sure. Can you hear me well?
Yeah.
Yes.
Wonderful. Can you see my slides? Okay. So hi everyone, I'm very happy to be here. My name is Roy. I manage the product analytics group and the data guild at Waze, which is essentially composed of most of the data services you can think of that Waze has. Today I'm going to talk to you about how we see at Waze the transportation ecosystems as an economics and data science challenge, and how we approach this problem of trying to eliminate traffic altogether. So if the previous presentation by Boaz discussed how we utilize technology for autonomous vehicles, the approach that Waze goes into is quite agnostic to whether there would be autonomous vehicles riding the streets or not, because the problem is mostly about infrastructure as we tackle it in this domain. So how can you think about transportation as an economic problem? So in economics, we like to think about everything like in supply, in terms of supply and demand. What is supply in the field of transportation? Think about the x-axis is the number of drivers that you have on a segment, and on the y-axis you have the price or the crossing time of that segment. So supply, marked in the red curve, is essentially the relationship between those two, or it's the physics of the road, which I'm sure many of you are familiar with. And so in the beginning, when you don't have many people on the segment, then you have free flow speed. And then starting from around here, traffic starts to pile up, and as you probably know, traffic piles up very quickly. Now, you can also address this as a social problem where people do not understand the externality that they're giving everyone in society who are coming after them in the road. And I've plotted here also the marginal cost that is being bared by each additional driver that takes the road. So that's on one side of it. How can you manage the supply or affect people's affinity to go on the road based on the supply, and by getting them to realize the problem of them generating more traffic? You can place HOV lanes, for example, which places different prices according to the time that, according to whether you're taking your car alone, or whether you're carpooling with someone or taking the bus and so on. You can place congestion pricing. So in some places when there is high traffic, then it will cost you more. But these are the kind of mechanisms that are usually being deployed in order to get people to realize the externalities that they are generating. On the other side, you have everything that has to do with the demand, meaning user preferences or people's preferences, if you will, and that's depicted here by the green curve. If I will tell you how much time or what is the cost that it will cost you to get from point A to point B in real time, then it might affect your affinity to drive right now. Maybe you will stay and work from home. Maybe you will carpool with someone, and then it will take you a shorter period of time. Or maybe, and the approach that we're talking about these days in Waze is about carpool. So getting the whole demand curve to be shifted downwards and to be more flexible, assuming that you're driving a coworker or a friend or someone that you're helping out with. It's a big issue to understand supply and demand in transportation, as in any economic problem, because even if you have big data, that's not enough, because most of the things that we observe are equilibria, meaning when supply meets demand. And even if you have data, this is on the right, this is the data that you see. So getting a grasp of what is the demand and what are user preferences is a big deal. While I think that understanding the supply is something that has been more or less a conquered field, and you see that if you will stand behind the wheel and open Waze, we can pretty much accurately tell you how long it will take you to get from point A to point B now. But making a prediction in a few minutes from now or a few hours from now, that could be more challenging. So what is the Waze approach to this problem? It's not only about the drivers and helping people out finding the path, the optimal path once they're behind the wheel, but rather it is like an ecosystem, which I think is very much in line with what this org that has organized this conference is about. It's about having an ecosystem where companies, governments, and communities and other various services are joining forces in fighting a problem that we all hate, right? Everybody hates traffic. It is a common enemy that we're all trying to eliminate. So governments are considering where should they deploy HOV lanes and whether they are effective or not, or placing congestion pricing. Companies want to have more efficient way of planning their employees' commutes and paying less taxation, which is unnecessary if they are being taking some of the costs of the congestion that is being generated by vehicles entering their campuses. And of course, users want to have an optimal way to get from point A to point B, not necessarily just for commuting, but and not necessarily if they have or don't have a car, but just finding the right way to get from home to work and back, and planning the road optimally. So this is an approach that we have in Waze, in which we are combining both the work with governments, with companies, with our users, which are fundamentally drivers and people which have cars, but our aim is to reduce the amount of people who are using cars to get on the road, to put on the road by either carpooling or by planning ahead the optimal time for them to leave. And there is a big difference between what we can do to help you using our routing service if you are just start opening up the app once you've entered the car, versus whether you allow us to understand your preferences and whether you are checking out the ETA 30 minutes before you leave home, or even planning a few hours ahead, or registering to a few behavioral nudges that will allow you to understand better the traffic congestion or whether you should be leaving or not. So it's not only about an optimal prediction task of ETA, which is what everybody knows Waze is about, but it's more related also these days to behavioral changes and helping people plan ahead. When should you leave home? Should you stop along the way and pick up a carpool, or is it better for you to commute directly to your work? Is it better for you to pick up errands on your way home or on your way to work? Nudging the demand curve in terms of trying to get people to try a different approach of how they commute is also part of the things that we're working on. So, for example, one of the major things that we see in carpool is that about 60% of the people who tried using carpool, they tend to go back to the service. So the biggest challenge is actually getting people to try it out, and afterwards they pretty much get addicted to it. Estimating, of course, the elasticities of what is the price that I would charge for an extra mile of detour, or if I need to leave home 30 minutes earlier in order to get to work 45 minutes earlier, is it worth it or not? So these are all sorts of personalized aspects of people's preferences that we are estimating these days, and this is the part of the new ways that we're working on. In this cycle, where we're trying to understand user behaviors and based on that adapt the product and serve the users with more user communications that allow them to know in real time the traffic conditions and to offer them additional services like carpool, then it requires a different architecture of how data is being utilized at Waze. And this is just a very high-level visualization of the Waze Data Guild ecosystem, of how we utilize both how we connect the back-end systems that we have into an experimentation platform that generates knowledge and keeps generating new experiments that are constantly learning about how users behave, raising new hypotheses about how can you shape traffic, people's affinity to carpool, or how to use Waze in a more meaningful way than just starting it once they lay behind the wheel. And so this is a new approach of how to connect BI systems, product analytics, data science, and backend systems, all through this circle of knowledge accumulation of the patterns, the local patterns of how people behave with their traffic. So here's one example of the data science behind the Waze carpool, and how it all connects both product analytics, BI, and machine learning on top of the GCP Google Cloud Platform system. And if you want to go into more more in depth to the technical aspects, then there is a blog post by Philip Ajiman from the data science team in my org talking about that exactly. But I'm going to give a very high level example. So in carpool, you have riders and you have drivers. And it works in a way that riders, when they enter the app, they tell us what is their general commute pattern, or we infer it, and then they get a list of potential drivers that they can commute with. Same goes with drivers. So the drivers, we learn their commute patterns, and we offer them people who they can go to commute with as a driver. So behind that, of course, the list is composed of a lot of machine learning that generates the lists that each one of them sees based on similarity of the routes, whether they've commuted in the past, whether there are people who are more engaged right now. And of course, there is the whole aspects of the economics and the pricing system that allows you to predict whether this detour is going to be worth it or not for the driver and the rider to commute together. What affects driver? Hold on one second. What do we see that affects drivers' decision whether to offer a rider to join their carpool? If I need to bucket those things, it's mainly about the detour, the amount of time, the estimated amount of time and kilometers that the driver will need to do, because this is not like an Uber where someone is providing a service to another person. It's not like a cab where someone picks you up from exactly where you've hailed the ride. In this case, there is somewhat of a bargaining between the driver and the rider, because each one of them gives up a little bit, so that there is a pickup that doesn't require the driver too much, and the rider will not need to walk too much. You do that, and you have actual drives that should have taken place because the driver should have taken. So with riders, it's pretty much the same. You have there are all sorts of considerations, whether they need to walk a lot, the social aspects, the cost, and in there you also have the aspect of security, whether they would also be able to guarantee a ride back. So there are a lot of aspects here which are not about an optimal prediction task, but also the social aspect and the software behavioral aspect. Let's talk a little bit about the algorithm that lays behind this. It's very interesting as well. So how do you start matching between drivers and riders? So you started by finding geographically relevant candidates. And then you need to build a routing plan, because then it means that we need to build a plan that the driver, how they need to detour, when will they pick up the rider, and the same thing with the walking for the rider. Once we have some list for every driver and rider, we need to pick up the top 30 candidates for each one of them. So this is an example in Kfar Saba region of the potential, if you commute from Kfar Saba to Tel Aviv, the potential people that you could pick up. Now think about it, it's not that easy to scale this kind of problem, especially if you need to consider in each time to build a plan of how the driver is going to pick up the rider and where they're going to work. So we utilize all sorts of both algorithms and simplifications in order to reduce this problem into something which is scalable. And we also need to use all sorts of cost functions in order to understand what is the adjustment or the how do you say, the relative importance of each additional driven kilometer of detour versus additional 100 meters that the rider needs to take. And of course, we learn it using machine learning and adapt it. This is learned per region. So in a more dense region, people would be willing to walk less versus in places where it's harder to get a carpool. Now note that there is also the aspect of sending and accepting. A driver can send an offer to a rider, but in order for the carpool to be accomplished, it depends also on the rider. They need to accept it and vice versa. So the ranking system ranks for each one of the sides the option, the likelihood that someone will accept if they will send, but also we need to rank it based on the sending probability as well. So the overall score that we generate, on which we generate the list that the list that you get, is based on the multiplication of whether you will send and whether, if you will send, whether the other person would actually accept. There are all sorts of challenges in terms of how to rank them. I'm going to skip that, but just reducing the biggest challenge is usually reducing the problem of the matching into something that can be trained and served in real time. As I explained earlier, we can skip that. Another problem is that there is the behavioral aspect of many people registering for the service, but they're not really active. So understanding whether someone is really serious about trying carpool or they're just they onboarded to the service and then they're not really going to use it. This is a big challenge that we're working on, because it's not only a problem that you have someone onboarded and they're not using the service, but it can also disappoint people who are offering that person a ride and they don't get a response. Once again, there's a lot of behavioral aspects here which are combined with machine learning. So just to conclude, the aspect which I find personally the most challenging and interesting in how we work at Waze with data is that it's not only about machine learning, but it's the software aspects of how to tailor both the insights from the behavioral aspects and the user experience research, all the way down to the algorithms that narrow down the problem into something that is solvable in real time, that we can offer users a service, and filling out completely the circle of from idea to machine learning model into production, back to new ideas, and updating that circle all over again based on the behaviors that we see, which in many cases cannot be learned just by machine learning, but also using a lot of user experience research and product analytics. We are applying this ecosystem not only in Waze Carpool, of course, but the same ecosystem and the same infrastructure is being used for our ETA. We're going to deploy within a few months a completely new ETA algorithm that relies on this infrastructure. All the ads that are being served when you're stopping at a headlight, they're also going to rely on this infrastructure and same logic. And a new expected service, which is trip suggestions, that is going to, when you tap into Waze, we're going to offer you directly what are the what do we expect you to be navigating, and shorten the amount of clicks that you need to do in order to find the route that you're going to take. That's it. If you have any more questions, this is my website. My contact details can be found there. And I think I'm out of time.
אז רועי, יש שאלה אחת, איך אתם, sorry, I'll rephrase it in English, one question. How do you collect the trips of people, and whether your sampling space is big enough to create these encounters?
So users, when users are logging into Waze, we have a pool of more than 130 million active users that are using Waze as a navigation app. That's a very large top-of-the-line funnel for getting people to carpool. And of course, it's all, you know, explicitly, the user explicitly gives us that information. It's not it's only when they register to Carpool, then we utilize that information.
No, the question was about the size of the sampling space.
How do we reduce the size of the space?
No, if it is big enough to find enough matching.
So it's all about liquidity and density, right? If you have enough users that are willing for a specific spot or showing intent for a specific time frame to take a ride, usually it's around commute hours. So it's usually pretty much dense around 8 and 9 a.m. and on the way back at starting from 4 to 5, right? So density there is pretty easy to generate. And of course, you know, in the beginning, you have some routes where you have more sparse data and users, and then you need to bootstrap it somehow. So sometimes you subsidize it, sometimes you offer to people a longer detour or more walking distance just until you bootstrap that market. But that's any growth strategist will tell you that in the beginning, it's how to pick up the market in terms of liquidity.
Okay, thank you very much.
Thank you.
If there is any further question to any one of the speakers, you can do it now, I suppose, Freddie. We have a few more minutes.
Yes, we can, if there is some question. Otherwise, we are finished with the program, and it was very, very interesting. And I wish to thank all the presenters for their very interesting presentations on a very beautiful and wide variety of topics that covered a lot of aspects of bringing smartness to transportation. Thank you.
Thank you. Have a great day.
Thank you very much. Thank you very much.
All right, thank you all. Bye-bye.
Thank you. Bye-bye.